Hello. Today we're going to be talking about summations and proof by induction, which are an integral part of being able to understand the efficiency of the programs you're writing. This right here is the document cam that you're seeing down there. No cat cam today because in lieu of a whiteboard, we're document camming. All right. So let's go over to the Chrome machine. Whoops. Oh gosh. Try not to stumble over stuff. All right. So, what we're going to be doing today is talking about summations. And summations, I'm going to just start off with a bit of a confession. Summations kind of make me a little sweaty. They make me a little nervous when I'm reading a paper or doing something and I see a summation. As soon as Greek letters start getting involved, I get a little nervous, right? But I've gotten more comfortable with them over the years for a variety of reasons. Just seeing them a lot, but also I've learned some strategies and tactics I'm going to share with you guys today, so that when you see summations, you won't think, "Uh-oh, I don't want to be here no more." So what is a summation? A summation is just a way to count up a series of numbers, or particularly to count up the value of a function of a set of like function values. All right. So for instance, here we have, let's get the pointer. Here we have n, right? So this is the function n. And we're saying for the values of n from 1 to 4, what is the sum of those values, right? And I could do n squared, n cubed, log n log n, so on and so forth, right? And I could say from some fixed point to another point, what is the sum of those things? And so if we expand it out, over here we have 4n from 1 to 6, right? Equals 4 times 1 plus 4 times 2 plus 4 times 3 plus 4 times 4, blah, 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 blah. So we get 4 plus 8 plus 12 plus 16 plus 20 plus 24 equals 84, right? So it's just a really succinct way of writing a big set of additions. So we've all been adding since we were quite young. So as scary as summations can look, we should just remember that it's a lot of addition and to chill out. Later on, you'll see a big pi in the place of this sigma for the summation, and that is used for product. And it's the same idea. It's just instead of plus signs between each term, it's multiplication signs. As a programmer, I like to translate every summation I see into a for loop because that's just kind of how that's the way that I'm most comfortable expressing these kinds of things is through programming rather than just seeing those symbols there. It really helps me digest what's going on if I look at it as a for loop. Another useful reason for turning a summation into a for loop is that when you're trying to evaluate the efficiency of code you've written, you're going to have a for loop or a nested for loop or any of these other things, and you're going to have to do the reverse operation. You're going to have to turn that for loop into a summation so that you can then, you know, look up and find out or try to tease out of your brain or do some algebra to figure out what the actual efficiency of your software is, okay? So if we look here at this loop, we're just making a sum variable, and we're starting from 1 to 6, which means that we're doing this one on the right here. And we're saying from 1 to 6, just add to the sum 4 times I. That's it. That that's all these scary things are, right? And so whatever's in this little what to sum thing is what's going to be in this on the right side of this plus equals. That's it. That's all there is to it. It's not actually that bad. It's just, I think it's a little overwhelming at times because it's a lot of information packed into an itty bitty space, which is really nice and efficient when you're, writing on a chalkboard. But, also seeing this for loop is helpful to people like us. So why do we care about summations? I kind of got blindsided by a lot of summation work when I took algorithms as an undergraduate. The professor I took algorithms with, we spent like the first few weeks doing a lot of stuff with summations, and I really, really struggled. And algorithms made me very, very nervous with that, even that starting point. But and I kind of didn't even really know, like it seemed like kind of an out of left field. Why are we talking about summations? It didn't seem to fit in with everything else. And so since then, I've discovered the reason we talk about summations. And the reason we talk about summations is because when we're doing asymptotic analysis to determine how efficient our software is, we're looking at loops, right? When we had that asymptotic analysis lecture, we're looking for loops and nested loops and things like that, right? And so loops and iteration in general, so for loops, while loops, and recursion, those are the big ones. For loops, while loops, and recursion are going to be more or less how we determine the efficiency of our software. And so mathematically, the tools that you use to model that iteration, the for loops, while loops, and recursion, are summations. So once you can take your code and turn it into a mathematical equation, you can do all this cool stuff with summations to simplify the summations and then hopefully derive what we're going to call a closed form. And the closed form means you basically are going to turn what has the sigma summation symbol, this thing, what we have here, this summation, into just like a function, like a normal function, like n squared plus 3n plus 5 or something like that, right? No summation there. That's like closed form. You don't have to be adding things over time and so on and so forth. Something you also learn how to do in one of the calculus classes. Anyway, so here's an example of why it's useful to put the speed of your code into summations, is you can actually use some fun adjacent mathematical properties. Like here we can break 4 plus 3i into two different summations, and then here we have this 3i, which we can actually pull out entirely because of the distributive property, right? If I have 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4, that's 3 being multiplied by each term of an addition. And so you probably remember from way back, maybe you don't remember, but remember from way back that distributive property where you can actually pull that common term out of the addition, out of that thing, and pull it out to the side. And so that still holds for summations, because summations are just big, long additions. So you can do all of this stuff, which then lets you use more powerful mathematical tools to actually figure out what the efficiency of your software is. So the steps of the process are: turn your code into a summation, use algebra to come up with summations that you can work with, and then from there try to find a closed form. And sometimes the closed form, you just have to think about it for a little bit. Like, you can't just throw algebraic identities at it. You have to go and think like, well, what is this actually? What am I actually calculating with this summation? Which takes a little bit of thinky time, but don't just try to sit down and brute force it. Sometimes you have to kind of sit back and think like, well, what is this actually? Okay, so here we go. This is a special would you rather. This is a dangerously on topic and productive would you rather. Would you rather, when you complete your Bachelor's of Science, time rewinds to the first freshman day of class, except you have one more class's transfer credit than you did for the last rewind? Meaning, if I have to take, let's assume all classes are 3 credits and I need 120 credits, that means I have to take 40 classes. So you take your uh, so you take all of the things you need for a Bachelor's of Science, and then the next time you like time rewinds, and you get to do the whole thing over again, except you get to transfer in one more class than you did before the last rewind. So you do the full thing. then time rewinds and you come in with one class transfer credit, like one of your like English 100 or something. And then you do the whole thing again, and then time rewinds. It's like a really long groundhog. It's like Groundhog's College. And then you get there, and then you have two classes, maybe English 100 and Physics 1 or something like that. And so eventually time will rewind and you'll have all of your stuff transfer in, and you don't have to take it, and you just take one class. So your last semester is just one time. Or you have to take CMSC 341 X times, like some amount of times. So before we actually take a poll on this would you rather, we have to do what I do when I make these would you rathers, is try to figure out how to tune the second option so that it is as equally unpleasant as the first one, or pleasant depending on how you would view retaking your classes, right? So what is a choice that would make this a good would you rather? So how do we do this? Well, we have to come up for a summation for the number of credits. What would that be? And then can we come up with a closed form equation for that summation? All right. Okay. Let's try it. So I'm going to switch. Boop, boop, boop. Here we are. Ooh, base too big. Let's go live down over here. Boop. Excellent. Okay. So we have our paper. Blah. So we need 120 credits to graduate. We're going to assume all classes, well, not classes, are 3 credits. Okay, so 120 credits per class. So that's 40 classes. Excellent. So 120 credits, so we have to do 40 classes, which means, so how many classes, so how many classes would I need to take? How many classes in the Groundhog Day scenario? Well, the first time I'm going to take 40 classes, right? Then I rewind, and then I have to take 39 classes. Then I rewind again and have to take 38 classes. Then I rewind again and have to take 37. Right? You get the pattern here. So we're going to do the thing that I always hate because I feel like it's kind of hiding magic, but it's not hiding magic. It's just hiding 36, 35, 34 all the way down to the I'll have a rewind where I only have to take 4 classes, then I only have to take 3, then I only have to take 2, then I only have to take 1. Right? So how do we formulate a summation for this? So I'm going to pause, and I'm in tiny mode again, but pause. Okay. Hopefully you guys kind of got some of the answers there. Or like we had a good discussion or something. I don't know. I'm past Ben. What do I know? What do I know? All right. So let's look here. Well, this summation, it's 40. So summations generally go from a low value to a high value, right? We start at I equals, well, actually, let's say N. N equals something up to some higher value than that value. So we've looked at this, and this is 40. It starts at 40, and then it goes down. Well, then how do we deal with that? Right? How do we deal with the fact that it starts at 40 and goes down? Well, the nice thing about addition is it would be the same thing to flip this and say 1 plus 2 plus 3 plus ... plus 39 plus 40, right? It's still the same value when it comes out in the wash, so to speak. So we'll say that we'll start at 1 and we'll go to 40. Okay, so we have n equals 1 to 40. And then what are we summing? What is each term? Well, each term is just 1 to 40, so it's just n. It's just n. Hmm, interesting. All right. Sloppy cut. All right, back from a sloppy cut. Excellent. So here's our summation. So if we spend some time thinking about this, or working through it, or looking around our math textbooks, we find this is equal to n times n plus 1 over 2. Like, but what magic did you get? Figured it out. That it's n times n plus 1 over 2. And this is a, I think, oh, Eric Hamilton would know. If only I could summon him. I think this is the Euler summation? Euler? I don't know. Interesting. Anyway, so we get this. We say we came up with it, but we're not quite sure if this is the right answer, right? And if we plug this in, this is 40 times 40 plus 1 over 2. 40 times 40 plus 1 over 2, which is 40 times 41 divided by 2. So for 40, this maps out to 820. So that is 820 classes. Oh! So, going back to the would you rather for now. Back to the would you rather. Maybe. Maybe not. Would you rather? Okay, so then our answer is 820 times, right? Because that's how many of your overall bachelor's program you would take. And so maybe that would give you a starting point, right? That means it's the same amount of courses. Would you rather take the same course, 341, 820 times, or would you rather rewind and actually take also 820 classes, but I bet you thought that paused for a second. But you get to take different classes in that time. All right, so I'm going to pause here and we're going to talk about the would you rather, and then we're going to go on talking about proof by induction. I know everyone's super excited, so pause. And we're back. All right. Okay, so here's a slide that just reflects that what I wrote down here on paper. Excellent. All right, so let's get another sheet of paper. So we have this summation up at the top, so we're going to write this down. We're going to say so this is equal to this. But we were all question marks about it, right? So now we have to prove it. And how do we prove that? Oops, I didn't make it big. That's okay. I caught it fast enough. Boop. So now we have to prove it. So how do we prove it? So we're going to use proof by induction. So now that you've seen all this, let's go back to the slides, and we're going to talk about proof by induction. So proof by induction it's a proof strategy. There's proof by contradiction, direct proofs, proof by induction. More that I would know about if I was more mathematically trained. So what we do is we prove that a small version of the problem obeys our hypothesis, this thing that we're trying to prove. And then we show for all values greater than that small version, our hypothesis holds for n plus 1 if we assume it works for n. So let's look at, this is the anatomy. This is how all of your proofs by induction should work. And I will also say, this is probably not the first time you've seen this, but it's worth reviewing. Will you see it again in 441? Yeah, you sure will. So we're trying to show it to you a lot in a lot of different classes so that you have multiple times to get it ingrained in your brain goop. So you need a base case. And what the base case is saying is it works for a small version of this problem. Then you need an inductive hypothesis. Let's assume it works for a problem of size k, some k. We just pick a k, any k, whatever, just k. K could be 40, k could be a million, don't know, right? K. And then the inductive step is let's show that it works for either a one value larger or one value smaller than k. So can we move in like the in one direction, kind of up or down? Um, so mathematical induction. So this is from concrete mathematics. Mathematical induction proves that we can climb as high as we like on a ladder by proving that we can climb on onto the bottom rung, which is our base case, and that from each rung we can climb up to the next one, right? So we're showing I can get on the ladder, and then we could show at any rung that I'm on the ladder, I can step up one more rung to keep going. And this, you're seeing things like base case, inductive hypothesis, inductive step, and these might be ringing a bell or an alarm. It depends on the case. This sounds like recursion, and it kind of is. It's kind of a math way of like unwinding a recursion, which is yet another reason that we think that we teach this stuff is because it also cements your understanding of how recursion works, but in a more abstract way that's more divorced from the actual code. So let's do a proof by induction. Oh yeah, so we're just gonna finish out this lecture by completing this proof by induction. So let's go. The first thing we need is the base case. So bloop. So our base case we say for n equals a small value. What is a small value here? Guys? Guys in chat? There's no chat right now, but I know there will be in the future. Chat! Right? Think about it. What is a small value here? If you said 1, you're a winner. Ding! Alright. Then we need an inductive. So for any, no, we don't, not the inductive hypothesis yet. We're not done. For n equals 1, then what we're saying is n, no, so bloop, 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 n equals 1. This is 1. So I equals 1, and then I, which is just equal to, well, it's just 1 to 1, so it's 1. And then over here, we substitute it into this equation to say 1 times 1 plus 1 over 2. So this is 2 over 2. So all of these things are equal. Cool. So check, the base case works. Excellent. Cool. So then we're going to do the inductive hypothesis. And we're going to say, whoop. We're going to say, assume for k, we're just going to pick k. I don't know why it's always k, but we're going to say I from 1 to k of I is going to be equal to k times k plus 1 over 2. Okay, this is the hypothesis. So this is just an assumption. And this is us saying, suppose we're somewhere on the ladder, right? Suppose we're somewhere high up on the ladder, right? We're trying to prove it for n, but we're saying we're somewhere in we're at some point k. And so this is our inductive hypothesis. Our goal now will be to add 1 to k, because k is in these 3 spots, add 1 or subtract 1 from k, and make sure that this equality actually holds. All right, and it gets a little tricky. We're going to move on to a new piece of paper. Let's slide this up. Okay, so So we've assumed that for k. Excellent. So now we're going to do the step, the Stairmaster. Okay, so now we want to prove that k, so from I equals 1 to k plus 1 of I equals k plus 1 times k plus 1 plus 1 over 2. Okay? So that's what we're going to try and prove. So, what do we do? The answer is don't panic. So, we have to do something with the summation. This is stuff, this is just a function. I do this. This is algebra. This is just symbol manipulation. You're like, but algebra is really hard. Yeah, algebra is really hard, but we know how to do it. We've been trained to do algebra. What the heck's going on over here? And so now, this is the super secret trick. This is mega secret, so pay attention. This is super secret. This is super secret. I'm putting it in parentheses because whenever you talk about a secret of this caliber, you can't just leave it out on the page without some parentheses to hide it. These are like detection impervious shields here. So, we have the super secret thing, and the super secret thing is that what we're gonna try to do, our goal, we're also gonna hide this in parentheses. Our goal is to manipulate this equation to get something from the inductive hypothesis. Right? That's our super secret goal. This is the magic. This is the secret magic of proof by induction. Is we, especially when you have these summations, is we're trying to manipulate the sides of this equation to get one of these two things. We want to get one of these two things. And what that'll let us do is it'll let us substitute the other side. So if I can turn this into this and something else, like if this can be this and something else, then wherever I see this, I can substitute this in. We can't really do algebra as easily on these summations. So the idea is, well, let's turn this into having this as a term, and then I can substitute this in, and then ha ha ha, I feel very clever. So let's apply our super secret trick. I'm going to, because this is, I'm going to use the powers of folding to, this super secret trick is something, don't spread it too far and wide. Don't spread it too far and wide because it's incredibly powerful. So we're going to hide our super secret trick. Excellent. Whoop. It's so hidden. Where did it go? So I'm getting another piece of paper. Excellent. So we have this, and so what we're going to try and do is we're going to say I equals 1 to k plus 1 of I is equal to the left-hand side of the inductive hypothesis, because that's what we want to get. We're trying to get to that. I equals 1 of I. And what? So this is equal to this, right? This is equal to this plus what? What do I need to add to this? So if I have the answer to this for k, how do I get the answer for k plus 1? What do I add to it? Probably, excuse me, I'm going to burp into a pause. All right, so hopefully you guys have the answers. So this is actually just, This value here is k plus 1 higher. Right? Ooh! We did it! Right? So now we've applied our secret. So this is in, like, if you're reading this out of a textbook or out of Wikipedia, this is the magic. The rest of it, we're just going to do some symbol manipulation. So let's do that. So now, because we have this left-hand side, we can substitute in the right-hand side and get like equals uh, k times k plus 1 over 2 plus k plus 1. Okay, and if we multiply these out, we get 1 half, because there's a 1 half being multiplied here. It's like a secret 1 half. 1 half k squared plus 1 half k plus k plus 1. Oh man, did I mess this up? I sure hope I didn't. And then what we're trying to prove, get this back. This is very high tech. What we're trying to prove is that, so let's multiply this through. So k plus 1 times k plus 2. Well, k plus 1 times k plus 2 is, so over here, we have k plus 1 times k plus 2 over 2 equals k squared, 1 half k squared. So that's those terms plus 1 half k plus 1k, so plus 1 half k to multiply these two together, because that's still 1 half times this. Then these two together plus k, and then we get 1 times 2 divided by 2 is 1. Oh, we did it! We did it! We did the algebra, right? But so it's easy when you're trying to follow my algebra here, it's easy to lose track of the actual secret sauce, which was trying to get this term to exist from this. This is the hard part. This is the thing you have to think about. This is where you're like squiggly brain with your brain stem. That's what's going on here. The rest of this is just applying algebra. And it's so easy. It's so easy to get fixated on what's going on here that to lose sight of the fact that this is actually where proof by induction lives and happens. It's not down here in moving all these numbers around. This is accounting. Up here is where you're doing the clever, like, oh, I'm using the thing from my inductive hypothesis to sub these in. And that's where the magic of proof by induction lives. And here is my beautiful IKEA wood desk. All right, so that's it for class today. There's going to be a homework problem that's going to have you do some kind of proof by induction thing for a summation. And so half of that will be work together, and then the other half will be work independently. All right, so have a good day.